Hi, Ken Goodman here. Recently a client asked me to look into some rectification options for a low power widget powered by a couple of primary batteries. Let's look at this simple single loop circuit here, which I have pulled up in LTSpice 17. Wonderful software, by the way. Here I've got a 1.5 volt battery powering a widget modeled as simply a 1K ohm resistor here through a silicon diode to block any reverse current. It's pretty easy to analyze a single loop circuit like this and figure out what the currents and voltages are going to be, but let's let Spice give us the numbers. Okay, that shows our 1.5 volt battery. We've got roughly a 0.6 volt drop through the diode, so that there's only about 0.9 volts making it to the load. More than a third of the power drawn from the battery is being dissipated in the diode. That's horrible and usually unacceptable. What can we do about that? Well, let's start by using a Schottky diode. Oh, before I do that though, let's see what happens if I reverse this single battery. I'm not going to flip the battery around, I'm just going to change the sign on its voltage spec. Now what have we got? There's only about 2.5 nanoamps flowing in the reverse direction. Let's see what we can do if we replace that diode with a Schottky diode. Generally speaking, they're going to have a much lower forward drop than a silicon diode. The downside is often you may have to settle for a lower peak reverse voltage. Also, there may be significant reverse leakage current in that reverse battery case, and we'll look at that in a second. Just off the bat, in this case we're only dropping about 0.13 volts across the diode. So much less of the power drawn from the battery is going to be wasted in that diode. You know, that like 0.13 volt drop across that diode looks pretty good to me. Let's look at the reverse battery case. There's much more reverse current flowing in the circuit, flowing the wrong way through our widget, but still not enough to damage any reasonable device we might construct. Pretty practical solution in most cases. Every now and then you may have a really demanding application, or just a demanding customer, where that small voltage drop and the corresponding small reduction in operating time becomes a big deal. So that brings us to a little trick where we can use a MOSFET as a rectifier. Let me draw that circuit now. So here I've gotten rid of the diode and I've added an N-channel MOSFET in the low side. Now I could have added a P-channel MOSFET on the high side of the circuit, but generally speaking, N-channel MOSFETs are easier to obtain and slightly less expensive as a rule. What's going on here? This N-channel MOSFET, normally the way we would use it as a switch is we would put it in a circuit where it's blocking. We'd have it so that we want to turn it on to conduct in that direction, current flowing down through from drain to source only when the gate is energized. in this case, we've got it hooked up the other way. Typical N-channel MOSFET's going to have a body diode that's going to always conduct in the reverse direction. In this case, the reverse direction for the MOSFET is the forward direction for our circuit. The body diode is going to allow some current to flow in the normal direction in this circuit. Okay, but that body diode is typically going to be a silicon diode with something like a 0.6 or 0.7 volt drop. When that junction is biased on, it'll be perfectly happy to conduct in either direction, even the reverse direction, the same direction where the body diode allows current flow. But that channel has a resistive characteristic. Depending on the MOSFET, it might be anywhere from some milliohms to several ohms. Generally speaking, when you bias that transistor on, that resistor, that RDS on, is generally going to drop a lot less voltage at a modest current than the body diode would. Let's see how that works in this circuit. Let's just let LTSpice tell us what happens here. The current through the widget is almost 1.5 milliamps because the voltage across it is almost 1.5 volts. The voltage dropped across that MOSFET is something like 30 microvolts. That looks like an almost perfect rectifier. Let's see what happens if I flip the battery around. Let's just flip the sign on the voltage spec again. The current through the widget is like 1 microamp in the wrong direction. Well, that ain't gonna hurt your typical widget. And 1 microamp is not gonna drain that battery very fast. So that's all very good. But now let's get closer to what my client needed. I mentioned that my client was developing a device that was going to be powered by 2 primary batteries. Let's duplicate this circuit. And let's merge the 2 battery circuits at the rectifier output. 2 1.5 volt sources. I'm only dropping about 0.11 volt instead of like 0.13 before. But that's because there's less current flowing through each diode. Again, this is pretty efficient, only a little more than 1/10 of a volt dropped. Usually this is a pretty good practical solution, but it's not good enough for the client in this case. We want to wring every last drop of energy out of these batteries. So let's try to use our MOSFET rectifier trick here. This is where I came into the picture, by the way. Let's duplicate the MOSFET rectifier. And let's see what happens here. Okay, you know what? I'm going to name that node output so it's easier to tell what the heck's what when I bring up these simulation results. The output voltage is almost exactly 1.5 volts. Almost no voltage dropped through the rectifiers. Let's install both batteries backward. What happens? The current through each battery is only about 1 microamp. So, with both batteries installed forward, the widget works. With both batteries installed backward, the widget doesn't work, but nothing is damaged. Let's see what happens if one battery is installed correctly and the second battery is backwards. I've got 1.2 volts across the output. The widget's going to try to operate. The current through the widget is only a little more than a milliamp in this case. Let's look at the battery current. Holy mother of pearl. There's almost 14 amps flowing through the batteries. 14 amps, that's almost 14 amps of reverse current flowing through battery 2. Those batteries are going to be heating each other up and probably destroying themselves. Depending on the battery chemistry, there may be a fire, there may be hazardous substances released. In the actual application, these are going to be some kind of uncommon battery chemistry that's very long life for low power devices, but the batteries are actually considered too hazardous for a consumer to replace. So it would be a trained technician replacing the batteries, but with multiple amperes flowing backwards through one of those batteries and a much higher than normal current flowing, being sourced from the properly installed battery. Something bad is going to happen here. Why the heck is that happening? And what can we do about it? Well, the problem is our 3-terminal rectifier device here is relying on the absence of a positive voltage in the situation where the battery's reversed. But look at the MOSFET that's rectifying the output of the B2 battery. Even though B2's reversed, B1 is installed correctly, and it's putting a positive voltage on the output, which ends up turning on Q2 when Q2 should be off. There's probably a lot of ways to fix that, but here's my solution. So let's see what happens in this situation. Both batteries are strong, equal. They're both inserted correctly. I've got 1.5 volts on the output, almost 0 voltage drop across the rectifier, 1.5 milliamps flowing through the load. About half of that comes from B1 and about half comes from the second battery, B2. Let's flip both batteries. Well, there's almost no voltage across the load. The widget does not operate. There's no battery drain. Everything's looking pretty good here. Let's see what happens when one battery is installed correctly and the other battery is reversed. I've still got 1.5 volts on the output, so I'm still supplying 1.5 milliamps to the widget. All of that current is coming from battery B1, which is installed correctly. There's a tiny bit of leakage current on the order of a microamp going backwards through B2. Microamp, that's not really hurting anything. Now, one thing to think about here is what happens when one battery is slightly discharged compared to the other. Let's just say that B1 is slightly discharged. Let's just make it 1.45 volts. So it's a little weaker than B2. Let's see what happens. In that case, I've still got 1.5 milliamps being supplied to the device, but I've got a lot of current circulating between the two batteries. That's still not good. Why is that happening? Because there's not enough of a difference between the two batteries to bias this transistor off. Let me show you what I mean. Let's see what happens if this B1 is severely discharged. I've got 1.5 volts on the output. The device operates. I'm supplying 1.5 milliamps to the device. All of that current is coming from B2, which is still in good condition. There's only a microamp going through B1. All is well. So this more complicated MOSFET rectifier circuit serves us well in a lot of cases. It may be a good practical solution. When fresh batteries are installed correctly in the device when it's about to be put in service, it may be that the battery life will be slightly longer in this case than with the Schottky rectifiers. But you're never going to see any weirdness like the loop current between the two batteries with the Schottky rectifier. It just automatically takes care of so much, avoids so many possible problems. I'm voting for the Schottky configuration. I really want to wrap this up now, but I should at least mention that there are improvements you could make to this circuit. You might find an ultra-low power comparator IC that you could use instead of that transistor, and you might essentially reduce the threshold voltage to 0 with that IC substitution. Good day. Hope you enjoyed a video without my mug in it, and hope you'll be back soon.